The next speaker of today is Roy Barzel. He is from the University of Bremen. And today he talked about gravitationally induced entanglement dynamics and of photon pairs and quantum memories. So thanks, Roy. The floor is all yours.
Yes, thank you, Rick. So yeah, let me as well welcome you to my talk on gravitationally induced entanglement dynamics, photon pairs, quantum memories, as already stated. Yeah, I'm from the University of Bremen, and the talk, or let me state in advance, I'm working at the well-known and very beautiful drop tower in Bremen. And the talk is aligned with a recently published paper on arXiv from us. We published it with collaborators from Berlin, Mustafa Gündogan and Markus Krutzig, and yeah, together, of course, with my PhD supervisor, Klaus Lemmerzahl. And a very special gratitude goes to Dennis Rätzel, who was not only one of the creative minds behind the project, but moreover brought us together with the quantum memory experts from Berlin. So I first want to revise what gravitationally induced entanglement dynamics are, and then I want to prospect experimental paths how to witness this effect in an experiment by employing quantum memories and Hong-Ou-Mandel interference experiments, both ingredients which distinguishes our proposal from previous considerations. So first of all, gravitationally induced entanglement dynamics is nothing new. In particular, within the past decade, there was a vivid and controversial debate about this effect and all its implications, like decoherence effects, whether it actually takes place or not. And it was really exciting as a newcomer, yeah, to go into that topic. So what are gravitationally induced entanglement dynamics? It's explained here. So what you here see is a clock state, so-called clock state, coherent superposition of two energy eigenstates of the internal energy structure of a quantum system. And it has its name because during its time evolution, it precesses like a clock around the equator of its associated Bloch sphere. And so what we face here is a quantum mechanical notion of what a clock is. And this is really interesting because we know that time plays a very special role in relativity. Roughly speaking, counterintuitively, it's the case that time flows differently depending on how you move and where you are. So it's of very fundamental interest to study the behavior of quantum clocks in a relativistic setting within a curved space-time scenario. And this can be done within interference experiments like the Hong-Ou-Mandel interference experiment or the Mach-Zehnder interference experiment, whose interferometer arms are respectively placed in two different gravitational levels such that, roughly speaking, time flows there differently. And let me say, yeah, that we propose to operate these interferometers with photons, so to say, photonic clock states. In case of a Mach-Zehnder interferometer, it's a single photon in a coherent superposition of two frequencies. Ramelow showed that this can be generated, and Zeilinger showed the natural extension of a clock state to an entangled clock state with photons, namely frequency entangled photons. And for all those who are buzzed by mentioning the word clock and photon in a single sentence, don't worry. We propose to operate these interferometers with quantum memories. These are material systems which store the photonic information coherently and yeah, let it evolve in time and imprint the information at the readout process again to the photons, which can be read out at the detectors. So what we here face with the quantum memories are really proper clocks, yeah, which account for the proper time which they measure. They are massive clocks, and they are clocks which are separated over macroscopic distances and entangled. So this is a really interesting system. Yeah, and what I wanted to say more. Yeah, and you cannot achieve this with atom interferometry because there you cannot get so large spatial coherent superpositions. So what we can expect from these experiments? Well, in a Mach-Zehnder case, it was already done, yeah, calculated by Züch, Brunkner and co-workers, and many others did it. This is basically done here, yeah, depending on the time which the quantum clocks, yeah, quantum memories, or as well photons, spent in the interferometer. The interferometric contrast erases. And the reason, therefore, is that the quantum clocks propagate through the interferometer, they get entangled, the clock state gets entangled with the path chosen through the interferometer, reveals the which path information, and yeah, of course, the detectors are frequency insensitive. If you trace out the internal degrees of freedom of the system, your residual state is a mixed state in a decoherent state, which does not anymore has any quantum properties, and thus no interferometric contrast anymore. Yeah, in a Hom case, it's something very similar. Yeah, in case of frequency entangled photons or entangled quantum memories, you can see this typical beating, quantum beating signal in the coincidence detection probability. So we can here see a change from photon bunching to photon anti-bunching and vice versa, depending on the time which the resources spent in an interferometer. And this is induced by gravity. And here the interpretation is quite similar. Yeah, because when photon bunching and photon anti-bunching is equiprobable, then no spatial correlation is present between the photons. And the reason, therefore, is, or between the quantum clocks, and the reason is that each quantum clock, while traveling through the interferometer, gets entangled with its path. And this entanglement can only be generated at the cost of lowering the mutual entanglement between the particles. This is the theorem of entanglement monotony. I need to break up the entanglement in order to entanglement between 2 degrees of freedom in order to entangle other degrees of freedom if the previous ones are maximally entangled. And this is precisely what is done with frequency entangled photons, which drive the quantum memories. All right. Yeah, let me state that operating this interference experiment with Hong-Ou-Mandel interference is better than Mach-Sehender, because yeah, you can see in the Mach-Sehender interference pattern, or simplified version of that, that the sum of the frequencies is present as a prefactor. And this leads in a real experiment to noise effects. Yeah, you can see it here. This high frequent oscillations could appear. They make it just harder to measure the effect in a real experiment. And this high frequent oscillation is not present in the Hong-Ou-Mandel interference pattern. And moreover, as you can see here in a factor of 2, the Hong-Ou-Mandel, the effect of desire happens twice as fast in the Hong-Ou-Mandel scenario, because because we here have 2 particles. Yeah, you can see it in this factor here of 2. If you have 3 particles, you can do it as well with 3 particles. Then it happens 3 times as fast. However, of course, it gets harder and harder to generate higher orders of multi-party entanglement. Of course, Hong-Ou-Mandel frequency entangled photons are not that hard. Okay, but let's take a look on the needed time to disentangle or entangle the quantum clocks with a space-time path. Yeah, so here is a result plot. Yeah, here's the needed memory storage time in order to infer or to observe a change in the a qualitative change in the detection statistics, which you can from this you can infer the entanglement properties of the system. So here we have the frequency separation, so the separation of the energies of the clock state, of the 2 states of the clock state. And the vertical lines correspond to different quantum memory types. Yeah. So for instance, ground state, lambda type quantum memories, extremely long coherence times, minutes up to hours, were already demonstrated. This is really amazing. When we heard this, we were really astounded. Yeah, and then another transition is at the optical clock. At optical frequencies, so hundreds of terahertz, optical clock transition, a remarkable storage time of 20 seconds. The different lines correspond to different redshifts. Yeah? These upper three are terrestrial experiments, small redshifts in the regime of 10 to the minus 14. The lower ones are space-based implementations, so you need at least one satellite. Higher redshifts, 10 to the minus 10. So of course, the stronger the redshift, the shorter the time the less time is needed, yeah, because redshift amplifies this effect, of course. All right, yeah, and here now the take-home message. Here is an intersection point of a terrestrial experiment of the Bremen drop tower, which can be operated with a quantum memory. The needed memory time to show up the effect, to reveal this effect, is around about 1 second, even less, yeah, 0.1 second. And as you can see here, optical clock transition memories can afford for that. So this is really interesting. This would be the next logical step to operate this experiment in order to reveal this effect. I see the time. I'm almost finished. Yeah, and one more very interesting intersection point is in a space-based implementation. There we can use optical fibers, yeah, of lengths of 6 kilometers, because the time, yeah, is we need 10 to the minus 5 seconds roughly to show up the effect, and 6 kilometers of fiber cable is enough. Yeah, in the other scenarios, so you cannot do this with 1 second because of the attenuation of the light signal in the fiber. Well, if you want to wait 1 second, you need 200,000 kilometers of fiber. Yeah, the speed of light is a little bit lower in the fibers. Yeah, 200,000 kilometers, absolutely impossible. Several hundreds of decibel loss, no chance at the exit of these cables, nothing will come out. Yeah, and this was basically, I think, everything I wanted to let you know. And so far, I thank you for your attention. I do not know whether time is left for questions, but yeah, I will also join Slack. Yeah.
Thanks, Roy. Yeah, we do have time for one question. So I see Igor there. Igor, please go ahead.
Yes, thank you very much. Yeah, very interesting. You know, I'm very interested, of course, in this direction. Good to hear.
I also like your work. I read almost everything.
Yeah, thanks. Yeah, I can see that, because you know, it's very exciting if there's a real implementation where I can do it. But I have some caveat I want to understand better, and maybe I missed in your talk. So so there's two problems, or no problem, but is your clock the photon that kind of is supposed to measure time, or the actual quantum memory? And in both of these, there's a caveat. If the photon is supposed to measure time, they don't feel proper time. So we had the follow-up in 2012 that showed you have to use the Shapiro delay, and there's a different scaling, so it's more difficult. And if it's the quantum memory that's supposed to measure, you know, tick log time, then there's a problem. You have now two of them, so you don't really have a superposition that you wanted to probe in the first place. So maybe to clarify that.
Yes. So yeah. So this is a very good question. Of course, yeah. There's of course a subtle difference, yeah, between operating this experiment with optical fibers and with quantum memories, because just as you said, in the case of photons, they do not measure the proper time, of course. However, they measure the optical path, and this is precisely what you say. It's basically the Shapiro delay what you account there, yeah. If the optical, so if you operate this system solely with photons, you only have these optical fibers, yeah, and you have to synchronize the delay time, so to say, in a different way, of course, than in case of the memories. Yeah, so this is absolutely right. And yeah, of course, you are also right when stating that the quantum memories are not in a spatial coherent superposition. Yeah, we have the memories at the cell. However, their internal states are entangled. Yeah, and these internal states, they account for the proper time, right? So we computed the effect of the quantum memories. You can read it in an arXiv article, and Yeah. Let me state. Maybe this answers your question. See, we have in each arm there are 2 quantum memories. So and these 2 memories, they they are resonant to different energies, to different frequencies, and either the one or the other is excited. So, and this has the same effect. Yeah, I hope yeah, I could answer the in some.
Yeah, sure. We can, we can take it further later, but it's, very nice to start a discussion.
Yeah, yeah.
So on Slack, you can see anyway, I posted that. There is a link to a paper about a year ago where we also discuss a very similar, well, it's actually a much bigger paper because this was part of a work of a science definition team for a future NASA mission. But one part there dealt exactly with the same kind of problem. So we was discussing this 2-photon interference, the gravitational redshift effect on a 2-photon interference experiments with frequency entangled photons. So basically would correspond to the case with no quantum memories. We were not focusing or not emphasizing that aspect there, but having this optical fiber as a delay line. Okay, so that was the case. And then trying to address Igor's question when he was saying a photon doesn't measure proper time. So we have a discussion there that I think is relevant, pertains to this question, and it's the following. In fact, to construct this properly, what you need to do is that you need to have a proper, so now you will see how proper time somehow arises there. You need to have a frequency reference or a clock that should be the same, ideally, to calibrate both delay lines on your spacecraft and on ground. So in that way, you use this local frequency reference. You have 2, one on ground, one in the spacecraft. They should be the same. For example, some atomic clock, based on the same frequency. You use those then to calibrate the, so to speak, proper length of that delay line of each one of them locally, the one on the spacecraft and the one on the ground. So you calibrate them with those clocks, with those frequency references to have the same proper distance. And then basically, the time that the photon spends inside that delay line. So you can think of the photon coming in, going around, and then coming out. And the difference between these two space-time events, coming in and coming out, that's the proper time difference that will play a role here. And the point is that because you have exactly the same, the 2 delay lines that were calibrated in the same way, okay, so that they should correspond to the same sort of local proper time, then you can relate the 2, and the gravitational redshift then, when you send the photon that was going through the delay line at the bottom and then send up, and finally have this 2-photon interference with this kind of Hong-Ou-Mandel interferometer for frequency entangled photons, then you can read the gravitational redshift, read it out from the interference signal. But you see the proper time was coming from this point that you have the delay line. Your photon is going, around this delay line up there in the spacecraft, and the other entangled photon in the pair is going around the delay line on the ground. And those had to be, to do it properly, those had to be calibrated with equivalent local frequency references or clocks, if you wish. And that's how you construct this photonic clock, if you wish, and you can measure then this gravitational redshift. And the proper time would correspond, as I was saying, to this point. You can imagine, roughly speaking, the difference between, or the space-time events that would correspond to the photon entering this delay line and exiting the delay line.
Sorry, Igor, before step in, let me just say, so this question is very interesting. However, it's already 12:20, and the next session is 40 minutes. So, Igor, if you could give a brief response to this.
Okay, I can be very brief, and yeah, I'll read it maybe more careful, but if I understood you correctly, I would still have the same worry, namely not just simply that how to measure proper time with photons. Yeah, there's different ways, that's true, but my worry with 2 photons would be then the following case, that what you're measuring is just 2 local proper times, and you're interfering them, whereas our original proposal was we want to go to a new regime you would like kind of to interfere proper time.
Yeah, so here, yes, you have to keep in mind that what he was presenting is not, as in the usual quantum clock interferometry, a single clock that follows two paths. What he has is two clocks that are there, so to speak,
Right.
but they are entangled. So basically what he's considering is that he has not a single clock in a superposition of two different, heights, but two clocks at different heights, and then they get entangled, and then you measure some interference effect where, as a result of the entanglement, but including the effect of gravitational redshift.